Good afternoon, everyone. This is Wade Sisson from Advanced Clustering, and I want to thank you for joining us today for this webinar. We're going to take a first look at the newly launched Rockport Switchless Network, which debuted right before Supercomputing last month. And we're joined today by some members of the Rockport team, and I would like to turn it over now to Pat Zolnier.
Great, thanks, Wade. Good afternoon, everyone. Hopefully you're having a wonderful day. We always are here at Rockport. So we, as Wade mentioned, came out of stealth mode here about the end of October, the 28th or 9th, something in that neighborhood, and announced our solution to the market, as well as announced our company to the IT world as well. We have been on an interesting trajectory since then, in talking with many customers like yourselves and explaining and evangelizing how we've completely changed the way the industry and we look at networks today. So one of the wonderful things we decided to do was ditch the switch, and you'll learn a little bit more about that from Loy's presentation to you as we move forward. Just a couple of housekeeping notes. Please feel free to use the chat window or actually, let's just use the chat window for any questions. We'll be happy to answer them probably at the end of the presentation so that we can keep the flow moving. And we only anticipate talking for probably 30-35 minutes. And then we'll go ahead and answer the questions. Hopefully some of them may get answered along the way, because that usually does happen, but we'll certainly answer any questions that we haven't addressed at the end of the session. So without any further ado, I'm going to turn this over to Loy Evans, one of our field CTOs, to go through and introduce you to the Rockport Network's switchless network architecture and solution. Loy, all yours.
Thanks, Pat. Appreciate it. Okay, so what I'm going to do is I'm going to just kind of give you a bit of an understanding of the why behind the founders of the company coming up with a new way to look at networking. What it really came down to is the switch architectures that you typically see in most data centers nowadays. Most of them are spine leaf architecture type of architectures, and if you understand a little bit of the history behind where spine leaf architectures came from, they were designed back in the 1950s, really kind of primarily as a design for public switch telephone networks. And while the architecture has actually been kind of appended, amended, enhanced, and tweaked a bit in order to make it a lot more performant, a lot more capable over the years, the problem is that the actual architecture itself has not changed. And so, it's, if you actually look at when you take a spine leaf architecture and start trying to scale it, there are these different breakpoints within these types of architectures where we typically end up with what I call the 49th port problem, where when you try to scale it from one point to another, you start hitting these stair-step functions in all kinds of facets of the network. Is stair-step function in more complexity, more administrative overhead, more costs, higher latency. And so, if you think about how a spine leaf architecture would grow, if you have a single switch at 48 ports and you want to scale that to the 49th port, typically you can't just drop in one more port or one more switch. You've got to go and drop in multiples. And there are these different stair-step function breakpoints that happen all around the types of scaling models for spine leaf architectures. So that was one of the primary, or those were some of the primary reasons why the founders of the company kind of started thinking, hey, can we completely and totally rethink how networking is done and remove a bunch of the pieces and parts that are directly responsible for those stair-step functions? So those were kind of the primary design features that we were going for when we started building the product. Now, along the way, as I mentioned, latency is a big part of what actually starts coming around. And as a bit of background, the chief scientist when the company was first started was a gentleman that was a PhD, worked in academia, and was very HPC focused. And so he was trying to figure out one of the ways in which we could address the problems that come in with parallelization. So if you look at kind of, Amdahl's law, where, hey, if you've got a process that can actually be done in parallel, when you parallelize it, it will run faster. But the problem is that just like in traditional networking architectures, there are certain breakpoints where you can scale up to a point where you start paying penalties for scaling beyond that. And so what we started seeing, and what the chief scientist started seeing, was once you hit certain levels of parallelization, every step beyond that actually increases the diameter of the network to the point where you're actually increasing latency, which in effect somewhat negates the possibilities and the opportunities of further parallelization. So the net effect is you're adding more nodes, but you're not necessarily getting more performance or more scale with the parallelization of those applications. So we wanted to try to actually take that and combine it with the architectural enhancements that we could use as the design goals for building a completely new networking product. So what we're introducing to the market is what we call a switchless network. And so what we've actually done is, in traditional spine leaf architectures, you always have top of rack and typically end of row, middle of row type of distribution of physical switches that do all of the work and have all of the intelligence for how a network communicates. Well, what we basically have tried to do is take all of those functions that sit within those switches, disaggregate it from the top of rack, end of row, from the actual physical boxes. Take the functions, disaggregate them, and actually embed them into the servers that make up the clusters. And so what we've done is we've taken this technology and we put it onto a network card. That network card actually has all of the functionality of a switch, and it allows us to completely distribute the routing and control planes to every single node in the cluster. Then we do basically a passive optical interconnect to where we directly connect that node with 12 other nodes. And so then those 12 nodes would then directly connect with 12 other nodes, which allows us to do a very distributed switching environment with extremely high path diversity. And we're removing the 49th port problem, those linear step functions in scaling a network. We add one more node, we add one more node's worth of bandwidth, and we add no more complexity in the network. And we have completely removed the actual concept of the external or the centralized switches in a traditional switching environment. So what this looks like is we basically have three components. We say that there's a three-step process to doing Rockport networking. That is, step one, plug a card in a server. Step two, plug a cable into the card. Step three, install the network manager, or ANM, autonomous network manager, easy for me to say. And essentially that is all that's needed. The card itself is basically, it's a 100 gig Ethernet interface to the node, to the host, and it is a completely standard based interface, right? So it's a open fabric enterprise driver that provides a standard Ethernet interface, which the main thing to take away from that is there are 0 kernel loadable modules and 0 custom drivers. So a standards based driver that actually needs to be loaded on the system, and that's it. As a matter of fact, if you were to put this into, like, say, a VMware box, you actually don't even have to install a driver of any kind. You don't have to install any extra packages. It is straight out of the box. The card will be recognized in forward traffic. And so we plug that card in, plug the cable into what we call a shuffle. So the middle box that you see there on the right, that looks like a switch. However, it is 100% passive. So it doesn't actually do, there's no power, there's no management, there's no software, there's no functional component in there other than basically just an optical fan out. And so what it does is, as soon as you plug a cable into that box, it is a pre-wired supercomputing technology. If anybody has ever heard of a torus network, out of the box, you plug that cable in and you're automatically a part of a 6-dimensional torus. And we'll talk a little bit about what that topology looks like in a bit. But it drastically simplifies what cabling looks like. And more importantly, again, there's no extra complexity there. All of the work is done in the card. Every single thing that comes from out of the card through the shuffle and to the next card is nothing but light pulses, nothing else. And so it drastically simplifies what you're actually doing. And then on top of that, if you've got a very compute dense environment where every rack unit is extremely precious inside the air conditioned cabinet space, we don't have any requirements for temperature management for the shuffle. So we've actually got some customers who are hanging these from fiber trays above the rack. So we're actually returning space back to the much more expensive real estate for doing compute in the conditioned racks. And then we have what I mentioned before, our A&M, which is an autonomous network manager that basically automatically registers all of the cards into it and then collects all of the telemetry from every single node. And then what it also does is, one of the first things, I've been in the networking business for about 26 years. This is probably the nicest network management system I've ever seen. And one of the really nice things about it is every single element of telemetry that gets collected actually gets charted on a timeline. And it allows us to actually go back in time to see what happened. Let's say we had an outage on a Saturday at 10 o'clock at night. We can actually roll the timeline back to Saturday at, say, 9:59 and actually watch what happened before, during, and after the event. And this is actually managed, mapped to alarms, events, telemetry on bandwidth, packet sizing, measurement of anything like that, all done on a timeline where we can see 100% fidelity of every single thing that happened over the last week. Once we go past a week, we still store statistics for up to a month, but it loses fidelity after that week time. But this is, again, the ability to actually do time travel and telemetry with 100% fidelity. And it's one of the best things that I've ever seen from network management. So if we look at just a direct comparison, if we look at what you would traditionally see in a regular network, where every single transceiver, every switch that you would see in the environment, if we have leaf and spine, or in some very large environments, you might have even a next layer of super spines. Every one of those things is actually going to require power, and obviously therefore require cooling. What we wanted to do from a design perspective was eliminate that. And so what we'll see in a Rockport network is the only thing in a Rockport network that requires power and cooling is the card itself. Once the cable is plugged in and the communication happens outside of the card, it is completely passive, and it is completely nothing but light pulses. So there is nothing within the environment that requires power or cooling. So it drastically simplifies all of those pieces. Now, I mentioned before that we are out of the box a 6D torus, a 6-dimensional torus network. And if you're not familiar with what a torus is, that's basically a set of multi-directional rings. So what you see on the right-hand side over here is an example of what's called a 2-dimensional torus, right? So now, again, we're 6 dimensions. This is 2 dimensions. And what you actually see here is the way that toruses are explained is in the the geometric directional axis, the number of nodes on each ring. So in this case, this is a 3 by 3 2-dimensional torus. So you basically have 3 nodes in the X dimension, 3 nodes in the Y dimension, and then basically completed rings on every single one of those. So this is a 3 by 3 2-dimensional torus. And just for reference, out of the box, our maximum topology with our first release product, which is out now, is 1,536 nodes in a 6-dimensional torus. And just like this is a 3 by 3, our max dimension is a 4 by 3 by 2 by 4 by 4 by 4, which would give us 1,536 nodes in a 6-dimensional torus. Now, from a behavior perspective, and how the actual network works is, when a node comes up, it will announce itself to all of its neighbors. And if you remember, we've got up to 12 directly connected neighbors. So the node comes up, actually sends out essentially a hello message, I'm here. And every one of those neighbors will then send back every single bit of topology information that they have back to the node that just came on the network. Well, that node now has all of the topology information that he needs or she needs to do a complete calculation of all possible routes to every other destination in the network. So as an example, let's say that we had a 1001 node network, just to make the math super simple for me. If we had a 1001 node network, The source would come up and actually learn all of the topology, then do a routing calculation for all 1,000 destinations in the network. Then we would store the eight best networks that go from that source to every one of those destinations. So at that point, we would have 8 active routes from that source to those 1,000 destinations. What this does for us is this allows us to be very quick in responding to some sort of a network event. So as an example, let's say that we've actually calculated out, in this case, this is a very simplistic example. I have tried to draw out a 6-dimensional torus in PowerPoint, and I can tell you it's an exercise in complete and utter futility. So a 2-dimensional torus works really well for illustrative purposes. And so in this 2-dimensional torus, we've gone in and calculated these 4 routes. Now, again, in reality, we calculate 8 from a source to a destination, but this is just a simplistic example. So let's say that we are talking from this source to this destination, and we're taking the green path, and then something happens on one of the nodes along the path. We will respond in hardware speeds, so within nanoseconds type time frames, to where, okay, green is no longer valid. I will immediately drop down to the next available path. Let's say that maybe it's the yellow path, and communicate across there. And so we respond almost immediately when there's a problem in the network. So this allows us to very quickly adapt to anything that happens in the network, to where we're not having to reconverge or recalculate in the event of some sort of a topology change. And so this allows us to actually react very quickly to any type of event that might happen in the network. And every single node actually has 100% understanding of how to get to every other node. So what that also does for us is we are completely distributing the routing information in the network, to where, let's say that we do have a node failure. The maximum blast radius for that node failure is obviously that one node, but we only impact 1/12 of the bandwidth to all of the directly connected neighbors. And that allows us to A, route around that problem, and B, back to the linear scaling capabilities, is that we have not dropped a significant portion, right? So if you've got a single switch network, obviously your entire cluster might be down if the switch goes down. If you've got, say, 2 and you're doing a redundant connectivity, well, now you've dropped 50% of the bandwidth from each host. So what this allows us to do is be a lot more capable of handling the resiliency of the network, while actually still serving the maximum amount of bandwidth possible, even in a failed situation. Now, at the bottom right, what you see here is basically what our underlying technology is. So we are seeing, again, we're an Ethernet interface to the host. We will see an Ethernet frame come from that Ethernet chip. Then what we do is we chop that up into some pieces called FLITs, or flow control units. We take those FLITs and we switch based on those in the network, switch or route, however you want to look at it. But we forward the FLITs from card to card to get to the destination. When it gets to the destination, we reassemble that one frame and hand it back up to the host. So what the host sees is a 100% completely unmodified frame or packet when it gets to the destination. So we're not doing anything on what actually ends up in the host. All we're doing is we're chopping that up. Now, if you remember correctly, I said from a design goal perspective, we wanted to try to change the calculus on how latency impacts workloads. This is actually the underlying technology of it. So we'll get into a little bit of the how we do that stuff. So basically, again, we're chopping things up into what we call FLITs. The main reason why we do that is because in traditional switch networks, we end up with a very common scenario, is that we end up with these smaller packets that are extremely latency sensitive. And if you're familiar with what most HPC networks use with MPI messages, where there are things like all-to-all collectives or barrier operations, things like that, which are extremely sensitive to not just latency, but extremely sensitive to tail latency, where if we've got, let's say, 100 nodes on a network, 99 of them respond to that MPI message in 2 microseconds or 2 milliseconds, but then it actually takes that 100th node 10 milliseconds to come back. Every single node in that thing has to finish that calculation before it can go to the next step. So the entire step takes 100 milliseconds. Well, what we're trying to do is we're trying to be a lot more fair for all different types of traffic sizes. And we're being a lot more fair with how we handle the arbitration of how things actually get into and out of an interface. So as an example, in a traditional switch network, if you have that latency sensitive, say 64-byte package, which is a pretty common size in a lot of those MPI collectives, where we have that, say a 64-byte message that gets jammed up behind either a 9K large data frame in Ethernet, or a 4K or a couple of 4K large MPI messages on InfiniBand. Well, no matter what QoS you have in place, that 64-byte message is going to have to wait its turn behind the 9K or 4K frame sizes. So what we're trying to do is we're trying to figure out a better way. And so through a bunch of different mathematical modeling, our engineers have come up with 160-byte flit size, and it is a variable length flit. So it's not all exactly 160, but it's a maximum of 160 bytes, where we will actually do basically fair queuing of the flits based on either when they come in, when the original frame comes in, or based on the priority, to where we can interleave those flits regardless of the actual size of the original frame that came in. So even if we were to get mixed in with a 9K data frame and a 64-byte MPI message, we have the ability to take that and be a lot more fair in how we treat that traffic, and therefore give a lot better chance for that latency sensitive workload to get queued in a lot faster. Now, again, if you just do the simple math, 160-byte playout on a 100 gig interface versus a 4K or a 9K frame on a 100 gig interface, there's a significant amount difference, right? It's orders of magnitude that we can get to that 64K frame and get that out of the buffer a lot faster. So based on that, what we've done is we've actually started doing some benchmarking. So we just came out of stealth, as Pat mentioned, at the end of October. And we have had product in customers' hands since before that, but we've been doing a lot of testing, benchmarking, and I'm going to walk through some of the benchmarks that you'll see. But I'm also going to talk about some of our actual customer workloads that we've actually done some testing on, and show you kind of what this actually means in real world. But if we look at the latency tests, right? In this particular case, we're talking about the OSU latency benchmark. And what we did was we designed a test to where we basically could completely congest all of the interconnect links between the spines and the leafs on an Ethernet network. And then we kind of contrived the network within our network to where we are completely congesting the same amount of bandwidth between the workloads that are doing the OSU latency tests. When we inject 100% congestion on a non-oversubscribed network within Ethernet, we're seeing that an Ethernet switch latency goes from about 2 microseconds when it's unloaded to about 22 microseconds. Within a Rockport network, we go from about 3 microseconds to about 3.3 to 3.5 microseconds. So about a 5 to 10% increase, not a 10x increase. If we compare that to like a 2-to-1 oversubscribed network, which is a fairly common deployment model, is we're seeing that a 2-to-1 oversubscribed Ethernet network will go from 2 microseconds unloaded to almost 120 microseconds loaded. Whereas again, we're doing the same modeling within our network, and we go about 5 to 10% increase in latency. Now, if we compare this to InfiniBand, now this is actually in comparison to a 200 gig InfiniBand, we're actually seeing that, again, the increase in latency is nowhere near the magnitude of an Ethernet environment. However, it is still extremely significant. So an unloaded InfiniBand network would start at about 2 microseconds, maybe just a touch below. But as soon as you inject 100% congestion on uplink bandwidth, you're actually seeing that they go up 5x to about 10 microseconds. Whereas on the Rockport side, again, about 3 to about 3.3 or 3.5 microseconds. So roughly a 5 to 10% latency increase. And this is consistent in almost every test that we're seeing. Well, so yeah, big deal, benchmarks. What does that actually really mean to an end user workload? Well, this is a workload test that was done by the Durham University in the UK, where they actually ran an HPC application code, where what they did was this was a 16 node cluster. Now, just truth in advertising, this is also 3 versions ago of software, right? So they actually were one of the very early adopters of this to do some testing. And this is the results that we got from the 1.0 beta. We've actually gone from 1.0 beta to 1.0 release, from 1.0 release to 1.01, and we are about to release our 1.1. And so this test, when run on some of the newer stuff, is actually going to perform even better. However, they have not done the software upgrades to their systems yet, so that's going to just be coming. But the numbers you see at the bottom there are the number of pairs of compute that are injecting congestion in the network. And so, the one on the far left is we ran the application on Rockport, and we ran the application on InfiniBand, just straight up, no, just 8 nodes doing the application. The one on the far right is we ran 8 nodes running the application, and 8 nodes sending traffic, basically being congestors. So 4 pairs that are sending congestion across that network. In that environment, the Rockport network finished the application code run 28% faster. And this is something that, again, we are starting to see this repeat itself in a number of different places. Another example of this is that we ran this with this is actually a GPU cluster running Google's open source trainer called BERT, or bidirectional encoder representations from transformers. But it's the BERT test that is an open source Google natural language processing testing. And you can see here that we had kind of a mix of some loaded and unloaded. And this is a 10 node cluster where the one on the far left is 4 worker nodes and 6 congestors. The one in the middle is 7 worker nodes, 3 congestors. The one to the right is all 10 running, the workload with no congestion. And what you're seeing is that, on this particular environment, the Rockport network ran anywhere from 19% faster to 38% faster. And again, I'm talking completion of the workload, not just pure bandwidth measurement or anything like that. This is, I started a timer when I started the workload, and I stopped the timer when the workload completed. The Rockport network allowed the applications to run almost 40% faster in certain cases. So this is where we're starting to see that, the models that we put together, where we kind of theorized very early on that, looking at this from the subframe assembly level and being able to more fairly interleave and more fairly treat different sizes and types of traffic, we thought that it would actually provide us some interesting workload benefits. And now we're actually seeing that it is actually showing up in a lot of different places. So the last thing that I want to kind of go through is just the economic and operational benefits that we're seeing. So now this, I'm going to go back real quick. The organization that we did this test with, it was actually a hyperscaler company. I'm not allowed to say the name, but from those people, they gave us what the cost of their GPU system cluster was, how much they expected the lifetime of that to be, how much they attributed the CapEx versus OpEx, and what the total cost per year was for that cluster. Then what we did was, we kind of just said, hey, let's think about, all right, you're investing that money, right? That OpEx and CapEx is you're committed to that amount. However, if you run a traditional network, and let's say on the low end, you're seeing a 19% slower workload completion time, how much more could you get out of your investment than with a Rockport network versus a traditional network? And so the math that we did was basically, okay, if you buy it with a traditional network that is going to run 19 to 38% slower, we essentially think that out of that $11 million that you're spending on the cluster, and out of the $4 million a year that it costs you to run it, you're wasting about 1.2 million to almost around 2.2 million per year of waste. Now, that we think that that's something that, is a realistic enough benefit that, we would like to see people putting this to the test and see if we can actually get it. We'd even like to see if there's a possibility that there are certain cases where if you've got a 64 node cluster, maybe you can run it with 56 nodes instead of 64. That's not 100% guaranteed that that's the case, because it will depend on the workloads and things like that, and also the mix of traffic. But we are seeing this repeat itself in a lot of places. And so we really think that there's actually a pretty significant amount of benefit there. Now, the last thing that I'll go through is just, kind of the footprint perspective, right? So I know that there's been a lot of discussion, in all types of media. There's been discussion in a lot of government organizations about the green side of technology and how to try to address what types of inefficiencies that we have in the market. Well, what we did was we just went in and we built out a redundant non-blocking 100 gig Ethernet network using GSA pricing. And we did a comparison of that to Rockport on, okay, cost, environmentals, weight, rack space, number of cables, all that kind of stuff. And essentially what we ended up, coming out in a model is we have a 60+% savings in power and cooling. Anywhere from 80 to, well, it's an 80% less space and 90% less weight, which, that doesn't seem like much, but there are certain environments where we've actually had, some customers say, oh yeah, we've got a data center up on the second or third floor. We actually have some pretty significant weight requirements for individual rack footprint. This would actually give those people the ability to, get more compute space in a single footprint than they can today. And then if you were building out the same type of topology, we're reducing the number of cables drastically. So this gives us some really interesting advantages when it comes to, and again, I'm not sure if anybody has looked into this, but there are certain things where, there's funding mechanisms for producing green technologies in the data center. There's other places where we're actually seeing requirements on businesses for making sure that they're taking the, looking at the ecological footprint of a data center. So this is some places where we think that there's actually some real significant benefit that can be derived from looking at a Rockport network as opposed to looking at a traditional spine leaf architecture that's been around for a long time. So, if there's any questions, we can open it up to the audience and see if there's anything that you're curious about.
So within the chat, I don't see any questions that were entered. If anybody has any questions, and Wade, I'm assuming you see the same.
I do.
Yeah, if anybody has any questions, feel free to, I don't know if I assume everybody's muted, unmute yourself and go ahead and ask any question to us that you may want. Cost information, any cost information. Generally speaking, yes, we are, having just come out of stealth, we're still kind of working through that a bit, but in reality, we are looking to be at, in essence, the same cost structure as an InfiniBand solution today, obviously with the additional processing power and carbon footprint savings, if you will. But generally speaking, and it depends, right? It depends if you're looking at a single switch solution in an InfiniBand or an Ethernet scenario, or whether it's redundant and you've got a spine leaf architecture. Typically, the more complex a spine leaf architecture you have, we become the value in the Rockport solution becomes much higher. So, the real, I guess the real answer to that question is, if you've got a cluster that you're looking at purchasing in the near future, we'd love to work with you through Advanced Clustering, who has been one of the first partners that came on board with us. They saw the value in the solution, and they actually have some equipment in their lab internally and doing some testing. So, we'd be happy to work with you individually through Wade and his team at Advanced Clustering to come up with a solution and cost out a solution specifically for your needs.
Okay. Does it work as a Rocky network? Yes, it does. Now, again, it's an Ethernet chip to the host. So obviously we can do Rocky V2. We can do, obviously IP. So, pretty much anything that you would normally see in that. And we also support a lot of the traditional offloads that you see for, either Rocky or Ethernet-based storage networks. So we can support a lot of different standards-based offloads as well.
Yeah, thank you for that question. Do we have other questions? Well, I want to thank everyone for their time in joining us today. And I just want to encourage everyone to, as was just said, Advanced Clustering has partnered with Rockport to be able to offer this in the clusters that we build. If you would like more information, you can contact us using the information on your screen, or you can visit us at advancedclustering.com and we'll be happy to get you a quote or more information. I want to thank everyone for joining us today. I want to thank Pat and Loy for the presentation. This is something we were planning to present to our customers at Supercomputing, but when that wasn't possible, we decided it might be a nice idea to present it in this webinar format. So we thank you for joining us. We have recorded this event and we will be sharing that with all attendees as well. I want to thank everyone who participated, and if there are no more questions, we'll go ahead and conclude the session.
Thanks, Wade. We certainly appreciate the opportunity to work with you and your customer base, and look forward to opportunities with your customers and working with you guys very closely going forward.
We look forward to
Absolutely.
that as well. Thank you, Pat, and thank you, Loy.
You bet. Thank you, everyone, for your time.
Thanks, everyone. Have a great day.
You too.